All right, so let's tackle our last example in section 2.1. So this is regarding resultant velocity. So this is example 210, finding resultant velocity. Okay, so an airplane is flying west with a speed of 425 miles per hour. Whoops, I wrote it is with these fours. 425. The wind is blowing from the northeast at 40 miles per hour. So what is the speed of the plane? And what is the bearing of the plane? So I'm going to be honest with you guys. I've already taken a look at this example, and I actually got the answer wrong because I misread it. This is saying that the wind is blowing from the northeast. Yes? I had done the example initially with the wind blowing to the northeast. This is what I'm saying, right? Those little teeny tiny bits of detail are going to make all the difference to making sure you're getting the right answer. So the other thing I have to do is actually look up the definition of bearing. Clearly, the speed of the plane is referring to the magnitude of our resultant vector. So the bearing of the plane, I would assume, means the direction. But I did decide that I wanted to look it up just to kind of make sure that I did know that that was exactly what they were asking for. So I don't know about you, but I'm not familiar with airplane terminology too much. So let's tackle this. Okay. Oops. Sorry guys, my whiteboard. All right, so I'm going to start off by drawing a picture. I'm going to throw in the coordinate plane for us to work with. Let me, oops, move that over. Okay, so we have that our plane is flying with a speed of 425 miles per hour. Okay. And we know also that the wind is coming from the west, northeast, I'm sorry. So that means it's blowing southwest with a speed of 40 miles per hour. So this is going to throw the plane off its track a little bit. And if we remember the parallelogram method, or whichever one you're more comfortable with, keep in mind then that basically what we're trying to do here is figure out the resultant. And so visually, the wind is going to throw it off track about that much. So our new sort of position of our plane is actually a bit south of what we thought it was actually going to. So we need to figure out what this new magnitude is, which would have, what its velocity is, which would have this magnitude, and also what that angle is from our x-axis. All right, so let's see. We know that the plane, let's see, I'll write it out this way. It's going west, just west. So West is our negative x direction. It has no y component, while the wind, now it has a perfect from the northeast. So that means the angle that we're interested in is that 45 degrees. So being careful here to just kind of make sure that we have the correct angle, we're going to use SOHCAHTOA once again. So this is our angle from the x-axis, from the positive x-axis. So the angle of the wind is perfectly southwest, which is 180 plus an additional 45 angles, right? So we're covering that whole positive half. Or you could say then it is negative 90 minus 45 as well. So it's up to you, 225. All right, so that has component 40 cosine of 225 and then 40 sine of 225. Okay. If you did the checkpoint, you should already know what that equals. Let's go ahead and compute it. So 40 cosine of 225 is just approximately negative 28. So I believe this is going to give us root 2 over 2. That 45 degrees tends to do this. Yeah, so negative root 2 over 2 or negative 20 root 2. And similarly, our sine is going to give us also a negative root 2 over 2. So let me see. Sine also has a negative component, and we've got the square root of a half, which is root 2 over 2. So negative 20 root 2. Awesome. So the resultant force then is the sum. Right? So that means that we're taking the sum of the x coordinates, so negative 425 minus 20 root 2. I'm going to use just my standard unit vector notation here. So that is my x direction. And then in my y direction, I've got the negative 20 root 2 j. All right. So we've actually increased the speed of our plane. This wind is pushing us in the same direction we're already going, so it's kind of giving us a little bit of an extra boost. So what is the actual speed of the plane? Well, the speed of the plane is the magnitude of the velocity vector. So it's the magnitude of our vector r. So we're taking the square root of this expression that we have summed the squares of our components in. All right, and so let's see what that gives us as a calculated value. Negative 425 minus 20 square root 2 quantity squared plus the negative 20 root 2 quantity squared gives us a resultant speed of approximately 454 miles per hour. And if we're interested in the angle of the plane, we can then once again take advantage of arctangent of our opposite over adjacent. So that's our y component divided by our x component. All right, so if I plug that expression in, we're going to get this 0.06. Now keep in mind that Desmos works in radians and our textbook works in degrees. So to convert to degrees, I'm going to multiply by 180 and divide by pi. All right, so we're getting this 3.5. And this should be fishy to us because angle 3.5 is over here, right? And we know that that's not right. And the reason for this is because of the repetitiveness of tangent, right? So tangent it has a vertical asymptote wherever cosine is equal to 0. And so what we need to do then is take care of the translation that would give us the same value. So, right, if we actually take a look at the graph of tangent of x, right, we see this repetitive notion. So when we're interested, we want to do then what's the opposite of that, and we can see that visually right here. So we want the 3.5 degrees to be below the west value. So we want to take a look at that. Below, right, so south of west, that's our final. Let's go ahead and take a look at the solution and see if we've gotten this right. All right, so they started out by taking a look at the plane velocity vector, which it called negative 425i. So they're using their components there. And then the vector with the wind has this positive angle of 225 degrees. All right, so they're starting off the same way that we did, finding that vector. So you notice that I rationalized my 1 over root 2, and I just left the square root of 2 in the denominator. This is a pretty common practice. I know in high school there was a very common request to rationalize things and not have square roots in the denominator, but as you get older, nobody really cares, I've noticed. All right, so we've taken our resultant vector by taking the sum of the two. We've gotten the same resulting vector that we arrived at right here. Fantastic. And then its speed is the absolute value, the magnitude of this, so the 454, we got the same answer. And then beautiful, angle 3.57 degrees south of west. And we've done it. All right, so why don't you try that checkpoint on your own? So in this instance, we're given information about wind blowing from the northwest. And can we determine the resultant information? So checkpoint 2.10, plane lies due north at 550 miles per hour. The wind is blowing northwest at 50 miles per hour. What is the ground speed of the plane? So find the speed of the plane. All right, so give that a shot before you move on to the next section.